If you are new to our channel, subscribe, like, and don't forget to share. Magnetic effects of electric current. Now, in this magnetic effect of electric current, first of all, we are going to deal with Bio-Sawart law because sometimes it is asked in 1 marks, 2 marks. Okay, so Bio-Sawart law. Now, what is this Bio-Sawart law? Let's say there is a current carrying conductor AB and the amount of current passing through this is I. Let's say we want to calculate magnetic field at point P, which has position vector R. Sorry. Here we take the current element ideal and direction of this current element is in the direction of current. The angle between current element and position vector is d theta. According to Bio-Sawart law, the magnetic field at point P due to this current element ideal that is directly proportional to current element. First, it is inversely proportional to the square of the distance of the point from the current element. Third, it depends on the sign of angle between current element and position vector. Combinedly, dB is proportional to ideal sine theta upon r square. Now, if we remove the proportional sign, this is mu naught upon 4 pi ideal sine theta upon r square. Now, this is the scalar form. If I talk about the vector form, in vector form, we will use the vector sign. It is mu naught I dl sine theta r cap upon 4 pi r square. Now remember that here r cap is not considered as a vector form. So we have to write the r cap as vector r divided by its magnitude. Okay. So combinedly now I can say the dB equals to mu naught ideal sine theta vector r divided by 4 pi r cube, and this is mu naught I. Now here you can say it is dl cross r, okay, and upon 4 pi r cube. So this is Bio-Sawart law in vector form. Bio-Sawart law in vector form. Now apart from this, the value of mu naught upon 4 pi is fixed, which is 10 raised to minus 7. Okay, and its unit is Tesla meter per ampere. Okay, that is the unit. I hope it is clear to everyone.
Sir, can you
Yes,
explain
sir.
the starting part again? I joined late, so
So if you join late, you have to suffer beta. Be on time. Okay. Why you were late? If you know the class will start at 9 o'clock exactly, and I logged in. Applications of Bio-Sawart law. Applications of Bio-Sawart law. Now, what are the applications? See, the first application is magnetic field at the center of current carrying circular coil. Now, let's say A circular coil is there, and this has a radius r, and here we take a very small current element. Let's say this is current element IDL. Now, can anyone tell me what is the direction of current element here? If the direction of current is anti-clockwise, any one of you, what will be the direction of current element?
Sir, away from the surface.
Tangential at that point. Okay. What will be the direction? Tangential at that point. Right? And the angle between position vector and ideal current element, that is 90 degree. Now from Bio-Sawart law, simple. We can write magnetic field due to this current element ideal at point P, let's say. It will be mu naught ideal sine 90 degree divided by 4 pi r square. Okay. Now sine 90 we know is 1, so it will be mu naught ideal upon 4 pi r square. Now if we need total magnetic field, okay, total magnetic field at the center. So for the total magnetic field at the center, we have to integrate this equation number 1. So integrating both the sides, now in right hand side, the constant parameters are mu naught I upon 4 pi r square. Mu naught I upon 4 pi r square, that is the constant parameter. Integration of dB is b. Now over here the integration of dl, if we say integration of dl, that will be the length of this circular coil, which is nothing but 2 pi r. So let's say this is equation number 2 and this is equation number 3. Substituting the value of this equation number 3 in 2, you will get b equals to mu naught I 2 pi r upon 4 pi r square. Now 1 r cancel, 2 pi 2 times cancel, so it will give us mu naught I upon 2 r. This is magnetic field. Okay, magnetic field at the center of the circular coil. Now sometimes we use this in terms of pi. So what to do? Multiply and divide with 2 pi. Okay. So this is proper way to write the expression of magnetic field at the center of a circular coil, current carrying circular coil. I hope it is clear to everyone.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, note down it quickly. Okay. Now see here, the third most important application we are going to do now, the magnetic field due to a current carrying circular coil at the axial point. Okay, that is very important. Okay, and out of these three, definitely one question, one derivation will be there in your final exams, board examination. So do practice again and again of these three special topics, right? Here we start with the next application. Application number 2. Magnetic field at the center of, magnetic field at the axial point of a current carrying circular coil. At the axial point due to current carrying circular coil. Now here so many things are very important. When we draw the diagram, you will come to know about that. So let's say this is a current carrying circular coil. Okay, and this is the center. Let's say its radius is capital R, and from its center at point P, axial point P, which is at a distance x from the center, we want to calculate the magnetic field. Now for that I will take a very small current element here, and this current element will be having tangential direction here, ideal. Now from this tangential element we will join the point P. So we will have the distance. The distance, let's say this is Q point, PQ. According to Pythagoras theorem, this distance PQ we can simply write equals to under root of x square plus r square. Okay. Till now, any problem, students?
No, sir.
No, sir.
Sir, very good. Now see the magnetic field due to this first current element at point P, okay, that will have the direction in this way, okay. Let's say this value is dB. Now for this, if I say this is phi, so this angle will be also phi, okay. Similarly, if I take another element here, identical element, okay, then it will also have the magnetic field at this point at the same angle if it is at symmetric position, just opposite to the Q element, and the value of magnetic field will be also same dB. Now let's say this is phi. Now this will both the magnetic fields dB, they will have components, two components. First component is this dB cos phi along y-axis, second one is along x-axis dB sin phi. Same way dB, first component is this one dB cos phi, and second component is along x-axis, which is dB sin phi. Now over here you can check simply dB cos phi, these two are same in magnitude, opposite in direction, they will cancel each other. The resultant magnetic field will be because of the sine components. So if I need total magnetic field, okay, total magnetic field at point Q, or sorry, P, at point P, okay, which can be simply find by integrating the dB sin phi, okay. Now our target is to find the value of dB and then sin phi. So here we start. dB, according to Bio-Sawart law, it will be mu naught ideal sin 90. Now here if I say the angle between this tangent and this position vector, that will be 90 degree. Remember that I am talking about the current element, and this, that will be 90 degree. And then 4 pi pq square will be x square plus r square. Let's say this is next equation, mu naught ideal divided by 4 pi x square plus r square. Equation number 2. Now the value of sin phi. Sin phi from this diagram, I can simply say r upon pq. pq is nothing but x square plus r square raised to 1 by 2. This is from the triangle OPQ. Okay. Substituting these two values from equation number 2 and 3 in equation number 1. So we will have integration mu naught IDL upon 4 pi x square plus r square and into sin phi. Sin phi is again r upon x square plus r square raised to 1 by 2. Now here the rest of the parameters apart from this dl are constant. So mu naught I r upon 4 pi x square plus r square raised to 3 by 2 as a constant, and only integration of dl is remaining. Now integration of dl, we know that is the length of this circular coil, which is nothing but